Hey guys, this is Coach Lowe, and this is Geometry, Chapter 2, and we're going to put sections 5 through 8 all together because they're all on proofs. And so we're going to talk about basic ways to set up two-column proofs. There's also paragraph proofs, which we'll look at later down the road. But two-column proofs, and then the reason why there are different sections, they cover algebraic, they cover segment, and they also cover angles. And so we're just going to kind of put those together. I just want to give you some exposure here with proofs, and then we'll continue on as we move through our book using proofs from time to time. So, again, Chapter 2, and then we're running through 5 through 8. All right, so the first thing is in 2.5, let's talk about some definitions. And the first one that I want to talk about is that a postulate, so if you hear the word postulate, so that you'll know what that is, or if they say axiom also, A-X-I-O-M, that's a statement that can be accepted as true without a proof. So a statement accepted as true does not require a proof. So W/O means without proof. All right, so in 2.5, there are several postulates that they give us, and they're on page 125. So when you get back to class, or if you took a book home, you can look at this on page 125. Postulates 2.1 to 2.7. You probably need to make sure that you know those. Now you're going to look at these and you're probably going to say, hey, I already know those. And that's totally fine. I hope that you do. All right, so I'll read through them, and you can decide whether you need to write them down. 2.1 says through any points there's exactly one line. We looked at that actually in Chapter 1. 2.2, through any 3 points there's exactly one plane. 2.3, a line contains at least 2 points. Postulate 2.4, a plane contains at least 3 non-collinear points. Remember, non-collinear means not lying on the same line. Some of you guys, or all of you guys, have taken your test over that already. We talked about it in the last chapter. 2.5, if you have 2 points that lie in the plane, then the entire line that contains those points also lies in that plane. 2.6, if you have 2 lines that intersect, then they intersect at exactly 1 point. That's their intersection, 1 point. So think about 2 lines, you draw 2 lines, or if you have a pencil and a pen, or 2 pencils and you cross them, they're just going to intersect at 1 point. 2.7, 2 planes intersect at exactly 1 line. So if you have 2 pieces of paper and you make those intersect, either you touch the ends of them or maybe you cut into one of them and slide the other one across, then you can see it would intersect in a line. Now, when we talk about conjecture, that is an educated guess that is based on given information. So conjecture, educated guess based on given information. All right, so we've looked at conjectures, remember, in 2.1 where they gave you a pattern, or they gave you numbers or pictures or whatever. You had to figure out the pattern, and then you had to make a conjecture about what that pattern was, and then write what you thought the next number was. That was a conjecture. You were making an educated guess on the information that they'd given you. All right, so now a proof, when I talk about proofs, those are logical arguments, and we back up those arguments with statements that we know are already true. Logical arguments that we back up with statements that we know are true. There goes my pen again. So back up with statements that we know are true. All right, so when we have a conjecture and it's proven true, so we made an educated guess, we proved that it's true, then it becomes a theorem. All right, so let's talk about how we do that. And I told you we have 2 different options right now, paragraph proof and a 2-column proof, and we're going to look at the 2-column proofs. All right, so let's check one of those out. On 2.6, just before we get to that 2-column proof, on 2.6, in 2.6 on page 134, there are several properties on that page that you'll need to know also. Probably want to write those in your notebook, and you can do that when you get back to school if you have a book at home. The addition property of equality says that if I have an equation like A equals B, then I can add C to both sides and it still remains equal. You will remember these probably from Algebra 1. These are things that you use all the time. If I add something to one side, I have to do it to the other. Subtraction property, if I subtract something from one side, I have to do it to the other to keep that balance, to keep those sides equal. Multiplication property, multiply by one side by a number, I have to do the same thing to the other side. And same thing for division property, dividing both sides by the same number. New ones would be reflexive property, and maybe you did talk about these last year, but maybe you don't remember them. Reflexive property says a number is equal to itself. Now this comes in handy, and we will use this as we move through our book. It comes in handy when you have a piece of a segment that's shared by two parts, and we're trying to prove that something's true, or like part of an angle, or part of a triangle, and you'll see this kind of as we move through this. Symmetric property. Symmetric property you use all the time. You probably don't even realize that you use it. You know, when you're solving an equation and you end up with 7 equals x or something like that, and you say, hey, can I flip that around? And I say, yes, that's fine. You can flip that around because of the symmetric property. So these are the same thing. Also, we looked at something this week where we wrote things like 90 degrees equals 5x plus 11. And then the question became, can I flip that around? And we said, sure, absolutely. You can flip that around to 11 plus 5x equals 90, or 5x plus 11 equals 90. Totally fine. So we can move those around because of the symmetric property of equality, or symmetric property, excuse me. All right, and then transitive property. All right, transitive property says if I have something like A equals B, and then I also know that B equals C, then check this out. If A is equal to B and B is equal to C, then I know that A is equal to C. So that is a transitive property. Deals with 3 different things, and then they have something in common here, like on this one, we had the B in common here, so that means A is equal to C. All right, so another one, distributive property, which you guys have used before, and the substitution property, which we've used before. Substitution property just says if A is equal to B, then in an equation I can substitute A for B. Wow, that's way down there because I can't see my marker, so that's awesome. All right, and then let's move on to the distributive property. The distributive property says if I have C times A plus B, what can I do with that? Absolutely. I can distribute the C through, and I can say C times A plus C times B. That's a distributive property. Those properties you've been using for a while. All right, and then there are also some other ones that we've already talked about. Segment addition property. Do you remember the segment addition property that we talked about, where if you have a segment and there are pieces to that segment, like A, B, and then C, that AB plus BC equals AC. So the pieces of this segment are equal to the whole thing. So from A to B, and then from B to C gives me the entire segment. That's the segment addition property. And then we also have angle addition property, where I could have 2 angles that are adjacent to each other. Move that one a little bit over here. So come on now. There we go. My pen is so awesome. Gotta love it. There we go. All right, so it says that I can take this angle, let's say that it's ABC, and then this point here is D. So it says I can add these two together and get the whole thing. So ABC plus CBD is equal to ABD. You guys have worked problems like that already in chapter 1, so that's a great thing. All right, there's also one more property that I want to talk to you about, and it's definition of congruent segments or definition of congruent angles. So really, it's a definition of congruent pieces. The definition of congruent pieces says if two pieces are congruent to each other, then their measures are equal. So sometimes in a proof, we'll have congruent, but we want to talk about them being equal so we can apply some of these other properties. And so we'll change it from congruent to equals, and the reason why you can do that is because the definition of congruent segments or angles or whatever you're dealing with. And so that's just another property you can kind of keep in mind that we will definitely be using. All right, so let's look at a statement, and here's the given. The given is negative 1/3 n equals 12. And we want to prove, so you'll have a given and then you'll have what you have to prove. We want to prove that n is negative 36. All right, now you may look at this and go, duh, Coach Lowe, of course it's negative 36. We can solve this pretty quickly, and that's awesome. But here's what we're going to do. We're going to take something that we already know how to do, and we're going to make a proof out of it so you can kind of focus on, hey, this is how we do this, and this is kind of cool. So here's the statement and here's the reason. And so we are going to solve this equation, and we're going to put the reasons why we're doing what we do. All right, so the first thing usually in a proof is the given. All right, so I'm going to write down what I'm given, and this is what I'm starting with, and this is the goal. This is where I want to stop. This is where I want to end up. So I'm starting with negative 1/3 n equals 12. And then for the reason, I just put given. All right, step number 2. So how would I solve this? Well, I want to get rid of the negative 1/3. So my options are divide by negative 1/3, or I can multiply by the reciprocal, which would be negative 3/1. So again, I'm going to do that to both sides. So I have negative 3/1 times negative 1/3 n, and I have negative 3/1 multiplied by 12. And this is this is multiplication property of equality. So in an equation, I can multiply both sides by a number, and it's totally legal. So that's what I'm doing. All right, then what's left? N on the left side and negative 36 on the right side. Okay, so why can I do that? Well, I substituted, right? I multiplied these two together, and I substituted n for all this junk right here because they are equal to each other. And then I substituted negative 36 for this right here because I multiplied those together, and negative 36 is equal to negative 3/1 multiplied by 12. So that's the substitution property. And by the way, I don't mind you abbreviating as long as I can tell the difference between subtraction and substitution and things like that, and I can read your writing. Don't make stuff up. All right. I think I just have one more for you, and then I'll let you practice some when you come back to class. So try to keep this video short, but again, we're covering several lessons here. All right, so here's my proof for you. And if you want to pause the video and try this, you definitely can. If AB, segment AB, is congruent to segment CD, then segment AC is congruent to segment BD. All right, so I'm going to draw a picture for you. Sometimes I'll have pictures drawn, and sometimes they'll be like, hey, draw it yourself. So this one, I'm going to draw it for you, though. All right, so A, B, C, and D. All right, so look what they're saying. If AB is congruent to CD, so I'm going to put those little marks on there so I remember those two are equal in measure. They are congruent, so you heard what I said. They're equal in measure. Probably going to be my first step is my second step, changing that from congruent to equal in measure. And then this is my goal. This is where I want to get to, right? So I have given the hypothesis of the statement is the given, and then the goal is, the conclusion is my goal. That's what I want to get to. That's my last line that I want to see. All right, so let's go ahead and make our 2-column proof here. All right, so here are my 2 columns. So when we make these 2-column proofs, I know some of you are like, oh my gosh, this is so annoying. That's okay. I don't mind you saying that. I don't really care, but I don't mind you saying it. Just kidding. It's just a way to organize your thoughts. Yes, you could probably talk through this and tell me, and that's great. This is just a way to organize that on paper because you can't really just, everybody can't tell me at one time. So great way to organize our thoughts. All right, so given. Segment AB is congruent to segment CD. All right, and this is my given. All right, now I'm going to stop and think about this for a second. This segment is equal to this segment. BC is obviously equal to itself. BC could be shared by AC, and then from A to C, that's BC, and then from B to D. All right, so if we can kind of incorporate that, then maybe we can show that AC is equal to BD because they share this segment on the inside. I'll show you what I mean by that. All right, so that's a given, and then I want to talk about AB being equal to CD because I want to be able to kind of manipulate this with my properties of equality. Notice they're not properties of congruence, they're properties of equality. So I want to change this from congruent to equals, definition of congruent. This time it's segments, right? Because we're working with segments, not angles. So definition of congruent segments. All right, number 3. BC is equal to itself. It's shared by 2 segments that I want to look at. So BC, I think I said congruent. I totally meant equals. BC equals itself. So again, the reason why I put that down is because BC is in common to both AC and BD. So we want to go ahead and establish that. And this is reflexive property. And something is equal to itself. All right, so the 4th one. I want to say AB plus BC is equal to AC, segment addition property. So AB plus BC is equal to AC. That's segment addition. All right. Hey, thanks for joining over here. No, get back over there. All right, number 5. Now I want to do the other one. CD plus BC is equal to BD. All right, so notice what these equations are sharing now. They're sharing BC. Okay, you guys see that? You catching that? All right. So let's do some subbing here. First of all, in this one, in number 4, I see that I can substitute CD right here because these 2 are equal to each other. So I'm going to substitute CD right here. Oh, let me write this one. This is segment addition property, so I'm just going to do a little whoop, whoop, and copy. All right. So number 6, I'm going to substitute CD right here. So I also know that because these 2 are equal, that CD plus BC has to equal AC also. Now look what I have. How cool is this? Look at this. CD plus BC is equal to BD. CD plus BC is also equal to AC. So that was, substitution. All right, so now what can I do? Remember what my goal was. AC is equal to BD. Can I say that now? Look, these 2 are the same. BD is equal to CD plus BC. And AC is also equal to that. So doesn't that force BD to be equal to AC? Absolutely. That's the transitive property, right? BD is equal to the same thing that AC is equal to. So transitive property. All right, now look what we wanted to get to. I have equals instead of congruent. So how do I change that back? Yeah, BD is congruent to AC, and I put the little line segment marks over it, and that's definition of what? Yep, definition of congruent segments. All right, and then I'll put this, or you can put QED. Finished. All right, look up what QED means if you don't know. All right, guys, I know that video was a little long, but again, we covered several sections with that. When you come back to class, I'll have a little activity for you to do, and it'll be awesome. All right, see you guys soon. This is Coach Lowe, and I'm out.